Hey guys, today we are going to be talking about those more proofs using those identities that we learned this weekend. So your essential question is, how do I prove trig expressions are equivalent? Basically, the only thing that's going to change is before on your problems it said you're taking this expression and you're turning it to this expression. So cosine x, tan x to sine x. Now they're just going to give you an equation and you're going to have to pick a side and figure out how do I make it say the other side. We are not allowed to switch sides halfway through because that can lead to some circular logic. So let's do a couple examples and kind of show how you can do these proofs, and they don't look like the proofs you did in geometry. Okay, so don't stress out too much. The first one we are going to start with is this guy. Secant squared x minus sine squared x secant squared x equals 1. So again, you have to pick a side and you have to stick with that side. And so my tip for you is to pick the more complicated side. I know I can write one a lot of different ways, but there's a lot of more stuff going on over here on the left side. So I'm going to go ahead and pick that complicated side. Now the one thing you can do here is, if you notice that you have a secant squared x in both of your pieces of your equation. So what I'm going to go ahead and do is I'm going to use that as a common factor and factor it out. So I have secant squared x on the outside, 1 minus sine squared x. Okay, and again, once I've picked this side, I'm trying to work towards this one, but I can't do anything to this one anymore now that I've started. Okay, if I remember from my identities chart, and again, you always get to use your identities chart, that I have a special property that says cosine squared x plus sine squared x equals to 1. If I went ahead and I subtracted sine squared from both sides, I would get something that looks very similar to what is in my parentheses. Okay, so again, you don't have to memorize these, but if you see a 1 and you see a squared term, you're probably going to use Pythagorean. So I'm going to have left over secant squared x, and then again, this whole parentheses thing is going to become cosine squared x because of the Pythagorean identity that we learned. Okay, now at this point, I could rewrite secant using the reciprocal and know that this is 1 over cosine squared times cosine squared x. And if you times straight across here, you would have these guys cancel out and you get 1. And that's what we were trying to find. So if you notice, we kind of left that side alone, and by showing this work, that is proving that this whole expression equaled out to 1. Okay, so again, once you pick a side, you have to stick with it, and if you can stick with the more complicated side, you're probably going to have more success in proving these equations. Okay, so let's try another one. Second one is 1 plus 2 tangent squared x equals secant to the 4th x minus tangent to the 4th x. Okay, so either of these sides would be okay to start with. However, I'm going to pick the one that looks a little bit more complicated because this guy has fourths in it. So I'm going to go ahead and start with my right side. Okay, so again, it doesn't matter which side you start with. If you start with this side, you could still make this equivalent. The first thing that I want to remind everyone of is we have some factoring stuff going on here. And we know something called the difference of squares. If you had a term squared minus another term squared, this would factor out to be x minus y, x plus y, because this switching the signs in between ends up making that middle term cancel out. So when I am looking at something like this, if I take the square root of whatever it is, so I took the square root of x squared, I got x, that goes first, then minus, then the square root of y squared is just y, and then you do the same thing again, you just switch the sign. So for this guy, if I take the square root of this, I know that secant squared x squared would give me this equivalent expression, and then same thing with tangent. If it's tangent squared x all squared. Okay, so I can rewrite this as a difference of squares, so that would get me secant squared x minus tangent squared x, again, square root of that, and then secant squared x plus tangent squared x. Okay, I know it seems like we made this pretty complicated. However, if you look at your Pythagorean identities, right here, we had the one with tangent and secant, okay, and if I went ahead and I subtracted tangent from that side, we would see that this whole term equals to 1. So secant squared minus tangent squared is just going to be 1. So I'm really just left with 1 times the part that's over here. So that was really nice of it. Oops, I don't know what is going on. Okay, whatever. We don't get a plus sign today. Okay, and so now at this point, you kind of have to look at what you're trying to get in the end. In this one, I don't have any secants, so I need to see how I can get rid of this secant. And I'm going to go ahead and use this identity again and know that if I went ahead and I subtracted, sorry, I know secant x, I don't even have to subtract anything. Secant squared x is just 1 plus tangent squared x. So if I replace this with 1 plus tangent squared x plus tangent squared x was still left there, and I went ahead then and combined like terms, I would have 2 tangent squared x's, and that's what I wanted. Okay, so again, doesn't matter which side you pick the one that's harder, and then kind of as you're going, look towards the other side and say, what do I really need to find here? And then kind of see if you can make that happen on the side you're working from. Okay, so let's go ahead and look at this last one. Again, we have 2 different sides, cosecant x minus cotangent x equals sine x over 1 plus cosine x. It does not matter which side you start from. However, I think that fractions look a little bit more complicated. And when we are dealing with fractions, we are going to use something that you have seen before, but I'm going to remind you of it, and it is called the conjugate. You used this in Algebra 2 when you were dealing with complex numbers and when you were dealing with radicals in the denominator. So if you remember, we were not allowed back in the day to leave this as your final answer, 1 over 1 minus the square root of 3. In order to get rid of it, we kind of use that difference of squares property, and I multiplied by the conjugate. Again, this is just a sneaky form of 1. I'm just timesing by 1. I'm not changing the expression at all, just timesing it by 1. And if you multiply this out, this would get you the first term, the middle terms would cancel, and then those square roots would cancel too. So, same thing happened when I had something with like an I in it. If I times by that conjugate, so same thing but with a different sign on the top and the bottom, so I didn't change the value, then that would cancel out that regular I term, and you would just have a normal number on the bottom. Okay, so remember, this right here and this right here, those are just sneaky forms of 1. You are allowed to times by 1, you are allowed to add 0, because it doesn't change the value of your expression or your equation. Okay, so to find a conjugate, you just keep the same thing, you just change the sign in the middle. So that's what I'm going to go ahead and do over here on number 3. I'm going to multiply by the conjugate. So I'm going to times top and bottom by the same thing, so it's just 1, and it's going to be 1 minus cosine x. Okay, and so now I'm going to go ahead, I'm not going to distribute this top term, not yet at least. And then if you have this guy, remember this, I'm going to write this right here, 1 plus cosine x times 1 minus cosine x. And so you would do some distribution here, or some FOIL, and what should happen is that that regular cosine term is going to cancel. So this would be sine x, 1 minus cosine x on the top, haven't changed that at all. Then I'd have 1 minus cosine x plus cosine x minus cosine squared x. Okay, so these guys go away, and I'm just left with something that might help me out. So if we remember my Pythagorean, because if you see here we have a 1, we have a squared, go to Pythagorean, and if I solved this guy out, the Pythagorean identity, I would know that 1 minus cosine squared is equal to sine squared. So I have this guy going on, this minus, and this is sine squared by the Pythagorean identity. Right? Now, if you notice here, one of the reasons I didn't factor it out is because I wasn't sure if something, or I didn't distribute, because I didn't know if something might cancel. And here it goes. Now it's going to cancel. There's a sign in the top being multiplied, and then there's 2 signs in the bottom, so I can get rid of one of them. Now what I have is 1 minus cosine x all over sine x. And remember, knowing your rules of fractions here is okay to split this up and have 1 over sine x minus cosine over sine x. They both have the same denominator. If I was to put this back over here, I would have the same expression. So knowing my reciprocal identity, 1 over sine x is cosecant x, and cosine over sine x is cotangent x. And that is what I wanted to find. So again, on these types of problems, the work is going to be your answer. We know what we want to get as our answer. We have to go back and make sure that we could get there. Okay? And so again, when you're proving things, it's just like what we were doing on 5.1. We've just gone back and said, now you have to pick where you want to start. This slide right here has some helpful techniques. If you want to pause and write these down, that's cool, but these are just some tips to do when you are trying to prove these guys. Okay, so that's all I've got for you today. I will see you in class tomorrow. Have a good day.